Here are some of the common Oracle wait events. DB file sequential reads. This event occurs when a user tries to perform a physical I/O while waiting for sequential reads from the buffer cache. This type of situation usually occurs when the data on the table is accessed by using index, not full table scan, as a result of single block reading. If this event occurs, possible reasons are wrong index usage, index fragmentation, excessive I/O traffic on specific disks. To solve this problem, query should use write index and rebuild indexes with a high clustering factor. Check indexes on the table to ensure that the right index is being used. Check the column order of the index with the where clause of the top SQL statements. Rebuild indexes with a high clustering factor. Use partitioning to reduce the amount of blocks being visited. Make sure optimizer statistics are up to date. Relocate hot data files. Consider the usage of multiple buffer pools and cache frequently used indexes/tables in the key pool. Inspect the execution plans of the SQL statements that access data through indexes. Is it appropriate for the SQL statements to access data through index lookups? Would full table scans be more efficient? Use write driving table? Goal is to minimize both the number of logical and physical I/OS. The Oracle process wants a block that is currently not in the SGA, and it is waiting for the database block to be read into the SGA from disk. Significant DB file sequential read wait time is most likely an application issue. If the DBA_indexes.clustering_factor of the index approaches the number of blocks in the table, then most of the rows in the table are ordered. This is desirable. However, if the clustering factor approaches the number of rows in the table, it means the rows in the table are randomly ordered and thus it requires more I/OS to complete the operation. You can improve the index's clustering factor by rebuilding the table so that rows are ordered according to the index key and rebuilding the index thereafter. The optimizer_index_cost_adj and optimizer_index_caching initialization parameters can influence the optimizer to favor the nested loops operation and choose an index access path over a full table scan. DB file scattered reads. A scattered read is usually a multi-block read. It can occur for a fast full scan of an index in addition to a full table scan. When performing a full scan into the buffer cache, the blocks are read into memory locations that are not physically adjacent to each other. To reduce waits on this event, optimize multi-block I/O by setting the parameter db_file_multiblock_read_count. Partition pruning to reduce number of blocks visited. Consider the usage of multiple buffer pools and cache frequently used indexes/tables in the key pool. Optimize the SQL statement that initiated most of the waits. The goal is to minimize the number of physical and logical reads. If statement access the data by a full table scan or index FFS, find out if an index range or unique scan. Be more efficient or parallel query improve the response time? Does the query use the right driving table? Are the SQL predicates appropriate for hash or merge join? The objective is to reduce the demands for both the logical and physical I/OS, and this is best achieved through SQL and application tuning. Make sure all statistics are representative of the actual data. Check the last_analyzed date. If an application that has been running fine for a while suddenly clocks a lot of time on the DB file scattered read event and there hasn't been a code change, you might want to check to see if one or more indexes has been dropped or become unusable, or whether the stats has been stale. Log file parallel write. The log file parallel write indicates the process is waiting for blocks to be written to all online redo log members in one group. LGWR is typically the only process to see this wait event. It will wait until all blocks have been written to all members. LGWR waits while writing contents of the redo log buffer cache to the online log files on disk. To reduce this wait, find out I/O wait on subsystem holding the online redo log files. Reduce the amount of redo being generated. Do not leave table spaces in hot backup mode for longer than necessary. Do not use RAID 5 for redo log files. Use faster disks for redo log files. Ensure that the disks holding the archived redo log files and the online redo log files are separate so as to avoid contention. Consider using no logging or unrecoverable options in SQL statements. Log file sync. This event is known as the time lost as a result of the LGWR process waiting while users initiate a transaction commit or rollback. If this wait event is occurring continuously, I/O performance of the LGWR process is probably poor, or commit is coming too often by the application. The solution to this problem is not to commit too much, if necessary, and to examine the I/O performance of the disk on which the redo log files are located, and to use a high-performance disk such as an SSD disk if necessary. Oracle foreground processes are waiting for a commit or rollback to complete. To reduce this wait event, tune LGWR to get good throughput to disk. For example, do not put redo logs on RAID 5. Reduce overall number of commits by batching transactions so that there are fewer distinct commit operations. Tune LGWR to get good throughput to disk. For example, do not put redo logs on RAID 5. Reduce overall number of commits by batching transactions so that there are fewer distinct commit operations. Buffer busy waits. This wait event happens when a session tries to access a block in the buffer cache, but it can't because the buffer is busy. That is, another session is modifying the block and the contents of the block are in flux. Buffer busy waits are common in an I/O bound Oracle system. The two main cases where this can occur are: another session is reading the block into the buffer. Another session holds the buffer in an incompatible mode equals. These waits indicate read/read, read/write, or write/write contention. The Oracle session is waiting to pin a buffer. A buffer must be pinned before it can be read or modified. Only one process can pin a buffer at any one time. This wait can be intensified by a large block size as more rows can be contained within the block. This wait happens when a session wants to access a database block in the buffer cache, but it cannot as the buffer is busy. It is also often due to several processes repeatedly reading the same blocks. For example, lots of people scan the same index or data block. The main way to reduce buffer busy waits is to reduce the total I/O on the system. Depending on the block type, the actions will differ. If it is data blocks, eliminate hot blocks from the application. Check for repeatedly scanned/unselective indexes. Try rebuilding the object with a higher PCTFRE so that you reduce the number of rows per block. Check for right-hand indexes that get inserted into at the same point by many processes. Increase initrans and maxtrans and reduce pts. This will make the table less dense. Reduce the number of rows per block. If it is segment header, increase of number of free lists and free list groups. If it is undo header, increase the number of rollback segments. Free buffer waits. This means we are waiting for a free buffer, but there are none available in the cache because there are too many dirty buffers in the cache. Possible reasons for this wait are: either the buffer cache is too small or the DBWR is slow in writing modified buffers to disk. DBWR is unable to keep up to the write requests. Checkpoints happening too fast, maybe due to high database activity and undersized online redo log files. Large sorts and full table scans are filling the cache with modified blocks faster than the DBWR is able to write to disk. If the number of dirty buffers that need to be written to disk is larger than the number that DBWR can write per batch, then these waits can be observed. Solution is to reduce checkpoint frequency, increase the size of the online redo log files. Examine the size of the buffer cache, consider increasing the size of the buffer cache in the SGA. Set disk_sync_IO equals true set. If not using asynchronous I/O, increase the number of DB writer processes or DBWR slaves. Ensure hotspots do not exist by spreading data files over disks and disk controllers. Pre-sorting or reorganizing data can help. NQ waits. This wait event indicates a wait for a lock that is held by another session or sessions in an incompatible mode to the requested mode. NQ wait could be because of various locks like TX transaction lock, generally due to table or application setup issues. This indicates contention for row-level lock. This wait occurs when a transaction tries to update or delete rows that are currently locked by another transaction. This usually is an application issue. TM-DML-NQ lock. Generally due to application issues, particularly if foreign key constraints have not been indexed. ST lock. Database actions that modify the UET used extent and FET free extent tables require the ST lock, which includes actions such as drop, truncate, and coalesce. Contention for the ST lock indicates there are multiple sessions actively performing. Dynamic disk space allocation or deallocation. In dictionary managed table spaces. Reduce waits and wait times. The action to take depends on the lock type, which is causing the most problems. Whenever you see an NQ wait event for the TX-NQ, the first step is to find out who the blocker is and if there are multiple waiters for the same resource. Waits for TM-NQ in Mode 3 are primarily due to unindexed foreign key columns. Create indexes on foreign keys 10G. Following are some of the things you can do to minimize ST lock contention in your database. Use locally managed table spaces. Recreate all temporary table spaces using the Create Temporary Tablespace temp file command. Cache buffer chain latch. Processes need to get this latch when they need to move buffers based on the LRU block replacement policy in the buffer cache. The cache buffer LRU chain latch is acquired in order to introduce a new block into the buffer cache and when writing a buffer. Back to disk, specifically when trying to scan the LRU, least recently used, chain containing all the dirty blocks in the buffer. Cache. Competition for the cache buffer's LRU chain. Latch is symptomatic of intense buffer cache activity caused by inefficient SQL statements. Statements that repeatedly scan. Large unselective indexes or perform full table scans are the prime culprits. Heavy contention for this latch is generally due to heavy buffer cache activity, which can be caused, for example, by repeatedly scanning large unselective indexes. Contention in this latch can be avoided implementing multiple buffer pools or increasing the number of LRU latches with the parameter db_block_LRU_ latches. The default value is generally sufficient for most systems. It's possible to reduce contention for the cache buffer LRU chain latch by increasing the size of the buffer cache and thereby reducing the rate at which new blocks are introduced into the buffer cache.